Hi everyone. Today we are going to study rooted and binary trees in graph theory. What are rooted trees? A tree in which one vertex called the root is distinguished from all others is called a rooted tree. So basically a rooted tree is just an extension of a tree. So, any such tree in which one vertex out of all other vertices can be distinguished from the rest of the vertices is called a rooted tree. And that particular vertex which can be distinguished from all others is called the root. Hence, it is known as the rooted tree. Below you can see all rooted trees with 4 vertices. This is a rooted tree with 4 vertices. This is a rooted tree with 4 vertices. This is a rooted tree with 4 vertices. And so this is also a rooted tree with 4 vertices. So basically all these 4 are rooted trees with 4 vertices drawn differently. And the root, as you can see in all the cases, is highlighted with a triangle. So this triangular portion represents the root of the tree, and hence this is known as a rooted tree. So you can clearly see this is one root from where all other vertices are branching out. One root, other vertices are branching out. One root, other vertices are branching out. One root, and then other vertices are branching out. So such a vertex from which other vertices branch out and which can be distinguished from all other vertices is known as the root. Such a vertex is known as a root, and any such tree containing such kind of a vertex is known as a rooted tree. Now generally the term tree means without any root. In general, when I say tree, that means a tree without root. However, for emphasis, they are sometimes called free trees. Just to emphasize the fact that they are not rooted trees, you can also call them as free trees. But when you call them tree, that itself means they are not rooted trees. So the term tree itself is sufficient to describe or to tell that this is not a rooted tree or a non-rooted tree. But to put emphasis on the fact that it is not a rooted tree, you can also call it a free tree. So when it is not a rooted tree, you simply call it a tree. And when it is a rooted tree, that means a tree with a vertex which can be distinguished from all other vertices. Usually this is that vertex from where all vertices are branching out, and hence it is called the root. So any such tree having such a vertex known as the root is called a rooted tree, and not all trees are rooted trees. So when I say tree, that means it is an unrooted tree, and when I specifically say rooted tree, that means it is a tree with a root vertex or a rooted tree. Now let's see what are binary trees. A binary tree is a special class of rooted trees, right? Just like a rooted tree is a special class of a tree. A rooted tree is a special class of a tree that we have just seen. And so is binary tree a special class of rooted tree. So a binary tree is a special class of rooted tree called binary rooted tree. So any binary tree is also known as a binary rooted tree, because if it is a binary tree, it has to be a rooted tree, because a binary tree itself is a special class of a rooted tree. So I can either call it a binary tree or I can call it a binary rooted tree. In general, we call them binary trees. A binary tree is a tree-like structure that is rooted and in which each vertex has at most 2 children. So as you know that a rooted tree has a root vertex. So obviously if binary tree is a special class of a rooted tree, so a binary tree will also be rooted tree. Obviously it is a tree-like structure that is rooted. And then when I say binary tree, the compulsion holds that it is such a rooted tree in which each vertex has at most 2 children. No vertex can have more than 2 children. They can have less than 2 children, but they cannot have more than 2 children. So every vertex in a binary tree has at most 2 children, and each child of a vertex is designated as its left or right child. So the child on the right side is known as the right child of the vertex, and the child on the left side is known as the left child of the vertex. And at most any vertex can have just two child vertices. So unlike a proper tree, the relative positions of the children is significant. Like in a general tree, the position of the children is not significant, but here the position of the children, which is usually signified as either left child or right child, that is significant. So position is very important here. If it is on the left, it is called the left child of the vertex. If it is on the right, it is called the right child of the vertex. A binary tree has exactly one vertex of degree 2. Another important property of a binary tree is that it has exactly one vertex of degree 2 and no more than one vertex with degree 2. So in the entire binary tree, you will find only one vertex with degree 2. And each of the remaining vertices will either have degree 1 or 3. Now this vertex which has degree 2, as I said, in a binary tree there is exactly one vertex of degree 2. So this vertex of degree 2 is called the root vertex. And that is another factor that uniquely distinguishes this vertex from the remaining vertices of the tree. So this root vertex has degree 2 and rest all other vertices which are the children of the root vertex will either have degree 1 or degree 3. Here you can see a binary tree, right? First of all, it is a rooted tree. You can clearly see this is the root of the tree, the root vertex of the tree. You can clearly distinguish this vertex from all other vertices. First of all, this is the vertex from where all vertices are branching out. Then this is the only vertex in the binary tree which has degree 2. Rest all other vertices will either have degree 1 or 3. Degree 2 means from this vertex exactly two other vertices are branching out, right? So hence the degree of this particular vertex is 2. So in a binary tree, the root vertex is that particular vertex which has degree 2. Here you can see a 13 vertex 4 level binary tree. 13 vertices, as you can easily count. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 vertices in total, so 13 vertex. And there are 4 levels in this. So the levels we will just discuss, but as of for now, you can clearly see this is a rooted tree since I have a root here, right? A root vertex here. Why this is the root vertex? Because this is the only vertex from where all other vertices are branching out. This vertex has not branched out from any vertex. This is the root of this tree. And it is from this vertex that all the remaining vertices are branching out. Hence it is the root. I can clearly distinguish this vertex from the other vertices. So clearly this is a rooted tree. Then this is a binary tree because here the compulsion that every vertex will have at most 2 children is being satisfied. This vertex has at most 2 children. This vertex has no children at all, right? At most you can have two children, but it is possible to have no children or just one child also. So this vertex has 2 children, this vertex has no children. This vertex again has 2 children, this has 2 children, this has 2 children. Then this has no children, this has no children. Then this vertex again has 2 children and this vertex again has 2 children, and the vertices at the bottom have no children, that is they are the pendant vertices. So that means every vertex in a binary tree will have at most 2 children, which is being satisfied over here, right? So this is a rooted tree. Then every vertex is having at most 2 children. So I can clearly say that this is a binary tree. Also, as I said, in a binary tree, there is only one vertex with degree 2. So you can see that which is the root vertex every time. So the root vertex, which is that one vertex, is having degree 2, 1 and 2. Rest all other vertices will either have degree 3 or 1. So if you see this vertex, it has degree 1, 2 and 3. If you look at this vertex, it has degree 1, 2, 3. If you look at this vertex, it has degree 1, 2, 3. Then if you look at this particular vertex, it has degree 1, 2 and 3. If you look at this vertex, it has degree 1, 2, 3. If you look at this vertex, it has degree 1. If you look at this vertex also, it has degree 1. So all the vertices either have degree 3 or degree 1, and only the root vertex has degree 2. So it clearly satisfies all the properties of a binary tree. So I can say that it is a 13 vertex binary tree. We will study the levels of binary trees also. For now, you see the vertex of degree 2 is distinct from all other vertices. This is what I just told you, that the only vertex with degree 2 is the root, and you can clearly distinguish it from all other vertices, and this vertex serves as the root. Now, thus every binary tree is a rooted tree, right? Because the very first thing that I said was that binary tree is a special class of rooted trees. So that means every binary tree is a rooted tree. That is, it is compulsory for every binary tree to have a root, which is distinct from all other vertices of that tree. Now, the properties of a binary tree. If you look at the properties of the binary tree, that is just the first property says that the number of vertices, which is denoted by n, in a binary tree is always odd. You will always see that whenever there is a binary tree, it will have odd number of vertices. Like if we see the example of this particular binary tree, we can clearly see there are 13 vertices. That means the number of vertices are odd. Just like that, if you look at other binary trees also, you will always find that the number of vertices in the binary tree will always be odd. So this is, why is that? This is because there is exactly one vertex of even degree. There is exactly one vertex of even degree. As I said, there is only one vertex in the binary tree which is of degree 2. Rest all other vertices are either of degree 1 or degree 3. So that means clearly there is exactly one vertex which is the root of even degree, and the remaining n minus vertices. Out of those n vertices, only the root is having even degree, and the remaining n minus 1 vertices are of odd degree. That means either they'll have degree 1 or degree 3. So that is the very reason why all the vertices of a binary tree are, the number of vertices of the binary tree are always odd. The second property of a binary tree says that if P is the number of pendant vertices, the pendant vertices means those vertices which are having degree 1. So if P is the number of pendant vertices in a binary tree T, then n minus p minus 1 is the number of vertices of degree 3. That means if n is denoting the total number of vertices and p denotes the pendant vertices, then the total number of vertices of degree 3 will be n minus p minus 1, right? So here we can look through this example also. Like here, if you see what is n, the n or the total number of vertices here is 13. Then the number of pendant vertices, you can see here. What are pendant vertices? Which are having degree 1. Like this is the pendant vertex. So one pendant vertex I have. Then this is a pendant vertex, second pendant vertex, third pendant vertex, fourth, fifth, sixth and seventh. So there are in total 1, 2, 3, 4, 5, 6, 7. 7 pendant vertices. So as per the rule, if I want to find out the number of vertices with degree 3, that can be found with the formula n minus p minus 1. So n is 13, p is 7 and minus 1. So 13 minus 7 minus 1 gives me what? It gives me, first of all, 6 vertices. It gives me 6 vertices with degree 3. Sorry, it gives me 5 vertices with degree 3. Now let's see if I have exactly 5 vertices with degree 3 or not. So we will just count the number of odd vertices with degree 3 over here, right? So 13 minus 7 minus 1 gives me 5. So that means these are the number of vertices with degree 3. Now the vertices with degree 3, let's start. This is the vertex with degree 3. 1, 2, 3. So I will highlight this vertex. This is the first vertex with degree 3. 1, 2 and 3. Then this is the second vertex with degree 3. 1, 2 and 3. So I highlight this vertex also 2. Then this is the third vertex with degree 3. 1, 2 and 3. So that means this is the third vertex with degree 3. Then this is the fourth vertex with degree 3. So 1, 2, 3, because 3 edges are branching out from this vertex also. So this is the fourth vertex with degree 3. Then if I look at this vertex, this is also a vertex with degree 3. You can see there are 3 edges branching out from this vertex. 1, 2 and 3. So this is also a vertex with degree 3. So this is the fifth vertex with degree 3. So clearly 1, 2, 3, 4 and 5. In total, I have 5 vertices with degree 3, and this is what it says, that the total number of vertices with degree 3 here is 13 minus 7 minus 1, which gives me 5. That means 5 vertices with degree 3. So clearly I can see if the n, that means the n if is the number of vertices, that means there are 13 vertices. P is the number of pendant vertices, that means if there are 7 pendant vertices, then the number of vertices with degree 3 will be n minus p minus 1, which in this case is 13 minus 7 minus 1, which is equal to 5. That means I have in total 5 vertices with degree 3, which I have just found. So this condition also holds for this. So this is the second property of a binary tree. Now a non-pendant vertex in a tree. A non-pendant vertex is one which does not have degree 3. So that which does not have degree 1. I'm sorry. A non-pendant vertex is such a vertex which does not have degree 1. That means it will either have degree 2 or it will have degree 3. So a non-pendant vertex in a tree is called an internal vertex. So any such vertex without degree 1 is called an internal vertex. So the number of internal vertices in a binary tree is 1 less than the number of pendant vertices. This is yet another property of a binary tree, that how many internal vertices will you have? The number of internal vertices in a binary tree will always be 1 less than the number of pendant vertices. Now clearly here you know the number of pendant vertices is 7. So how many internal vertices will you have? 1 less than the pendant vertex, which in this case is 7 minus 1, which is equal to 6. So that means we should have 6 internal vertices in this binary tree. We should have how many internal vertices? We should have 6 internal vertices. Let's see. As I said, all other vertices except the pendant vertices are called the internal vertices. So how many internal vertices I have? Now these vertices which are marked like this with a tick mark are the pendant vertices. These are the pendant vertices, right? All these vertices which are tick marked are the pendant vertices. Other than that, all other vertices are the internal vertices. Like this is the internal vertex. So I have 1 internal vertex, 2, 3, then 4, then 5 and then 6. So in total how many internal vertices I am having? I am having 6 internal vertices. That means if I do not include or if I discard the vertices which are tick marked, other than that all other vertices are the internal vertices. So 1 internal vertex, then 2 internal vertex, 3 internal vertex, 4 internal vertex, 5 internal vertex and 6 internal vertex. So how many internal vertices am I having in total? I have 6 internal vertices in total, which is the yet another property of a binary tree, that if you have p, if the total number of pendant vertices are p, then the total number of internal vertices will be p minus 1. So here the pendant vertices are 7. So as per the rule, the total number of internal vertices must be 7 minus 1, which is equal to 6. So here I can clearly see that how many internal vertices I have. I have total 6 internal vertices. So this is 1 internal vertex. This is another internal vertex. This is also an internal vertex. This is also an internal vertex. This is also an internal vertex. Then this is also an internal vertex. So how many internal vertices? 1, 2, 3, 4, 5 and 6. In total, how many internal vertices I am having? I am having 6 internal vertices. So this is yet another property of a binary tree, that the number of internal vertices in a binary tree is always 1 less than the number of pendant vertices. Okay, so now the distance of the vertex from the root defines the level of the vertex. As I told you when we were studying the binary tree, I told you that this is a 13 vertex 4 level binary tree, and I told you the level we will study a little later. So now we will come to the level of the binary tree. You know this is a 13 vertex binary tree, but how is this a 4 level binary tree? How do we find out the levels of the binary tree? So it is basically found by finding the distance of the vertex from the root. You know what is the root of the binary tree? You can clearly identify the root of the binary tree. So in this case, you know this is the root of the binary tree because this is the only vertex from which all other vertices are branching out. This vertex is not branching out from any other vertex. This is at the top, and all other vertices are branching out from this particular vertex, first of all. Then second, this is the only vertex in the binary tree which is having the degree 2. So these two properties make this vertex distinct from the rest of the vertices, and hence this is the root of the binary tree, right? And how do you find the level of the binary tree? By calculating the distance of the vertex from the root, right? So if this is the root, so obviously the root is always at level 0. Now the level of this particular vertex will be its distance from the root. So its distance from the root is of one edge. It is one edge apart from the root. There is only one edge between the root and this vertex. So that means I can say that this particular vertex and the root is one edge apart. Hence the level of this particular vertex is 1. I call it level 1, right? Then for this particular vertex or for this particular vertex, the distance of these two vertices from the root is 2 edges apart, 1 and 2. Hence the level of this particular these two vertices is level 2. Again, for these 4 vertices, 1, 2, 3, 4, the level of all these 4 vertices is how many edges apart from the root? 1, 2, 3. 3 edges apart. So the level of these vertices is level 3. Then if I look at the level of these 4 vertices, the level of all these 4 vertices, you can see that these 4 vertices are how many edges apart from the root? 1, 2, 3, 4. So I can say that the level of these vertices is 4. They are at level 4. So in total, how many levels are there? There are 4 levels starting from 0. Root is always at the 0th level. So 0, 1, 2, 3, 4. How many levels in total do we have in this binary tree? We have 4 level binary levels in this binary tree. So I can say that this is a 13 vertex 4 level binary tree. At level 0, you have just one vertex, n equals to 1. And n represents the number of vertices. So at level 0, you just have one vertex, which is the root. At level 1, you have 2 vertices. At level 2, you have again 2 vertices. At level 3, you have 1, 2, 3, 4 vertices. And at level 4 also, you have 1, 2, 3, 4 vertices. So I can say that this is a 13 vertex 4 level binary tree. And this is how you find out the level of a vertex in a binary tree.